An example of the integrating factor method. In a circuit with voltage V, an inductor L, and a resistor R, find the current I given the following differential equation. In the equation, we have L times di of t dt plus R times I of t equals V. First, we are going to multiply by 1 over L. We are left with di dt plus Ri over L equals V over L. In order to use the integrating factor method, we need a differential equation in the following form, which we have. Di dt corresponds to dy dx, R over L is P of x, and V over L is G of x. Now let's rewrite the equation using Lagrange's notation for clarity before we proceed. Next, we are going to solve for our integrating factor mu. Mu equals e to the integral of p of t dt, and r over L is p of t, so we can substitute that in. Now we can integrate, and because neither r nor L are functions of time in this problem, they are treated as constants, leaving us with mu equals e to the rt over L. From here, we will take the differential equation and multiply both sides by mu, our integrating factor. I showed that using the product rule, the derivative of mu times y equals mu of x times dy dx plus mu prime of x times y, which is what we have here on the left side of the equation. So we can rewrite the left side as mu times I prime. We can now integrate both sides and apply the fundamental theorem of calculus, which states that the integral of a derivative of some function is just that function, leaving us with mu times I. Next, we substitute in an expression for mu. V over L in this expression is just a constant, so we can extract it from the integral and integrate. We are left with this equation after integrating. Let's cancel the L's and divide by e to the RT over L to get the current by itself. The expression in the numerator can be split at the addition sign using properties of fractions. In our first term, e to the RT over L can be canceled. In the second term, the denominator can be expressed as e to the negative RT over L. Now we have a general solution to the problem. A general solution is a solution that includes arbitrary constants, such as C. If we want a particular solution, which is one without arbitrary constants, we need an initial condition. Let's say that at time equals 0, the current equals 0. This allows us to plug in 0 for I and t, and the exponent becomes 0. E to the 0th power equals 1, and we are left with C equals negative V over R. Taking these results together, we can replace our arbitrary constant to a particular value. So we substitute in negative V over R for C, and then we factor out V over R, leaving us with our final answer. I equals V over R times 1 minus e to the negative RT over L.